The Diamond Drilling Industries Inc. Complete Guide to PDC Drilling. Introduction. These guidelines provide drillers with essential information about how to prepare and successfully drill with a PDC drill bit. You will understand the drilling process, terms, and what to expect while drilling with a PDC drill bit, and how to adjust for variances in formations. PDC drill bit running procedures guideline for field engineers. While drilling a well, crucial decisions are made on the basis of what is believed to be happening downhole. There are a large number of factors that can affect drilling performance, from the drilling rig itself and associated surface equipment to the downhole equipment, from run parameters and formation type to their consequential effect on drill string dynamics and bit life. It is the purpose of this document to improve the understanding of the entire drilling system and provide guidelines so that the pertinent factors affecting drilling performance can be identified and managed. With better identification and understanding of drilling problems, informed decisions can be made to improve drilling performance and significantly reduce the drilling costs for our customers, the operator. These guidelines cover aspects of running a drill bit, from arriving at the rig site through to recommending drilling parameters, run recording and reporting. The guidelines can be used as part of the drilling optimization process, the plan, execute and evaluate cycle, to ensure a quality service is provided to the client. Whilst in the position of drilling optimization specialist for BP, Martin Fear developed two formalized drill-off test procedures for optimizing drilling parameters for maximum performance. Other reference material utilized was a drill string vibration primer written by Feridun Abbasian, also of BP. Rig Site Protocol. Evaluate the rig and surface equipment to become familiar with the maximum and minimum parameter variables that are available. An understanding of the limitations of the equipment can help in developing a realistic and practical solution to a drilling problem. Solids control equipment. Poor solids control equipment can cause the following problems. Ineffective or too few shakers can limit the speed at which cuttings can be removed from the mud system. If this is the case, penetration rate may need to be limited. If the solids are not removed from the mud effectively, the mud can become very erosive. Erosive mud can reduce bit and downhole tool life, resulting in shorter run lengths. If the solids content becomes too high, this can reduce the effectiveness of the mud, for example, shale inhibition with water-based mud systems. Evaluate the following equipment. Shale shaker specification. Number, type, screen or mesh size. Centrifuge equipment. Mud pumps. Mud pumps drive the mud around the drilling system. Depending on liner size availability, they can be set up to provide high pressure and low flow rate, or low pressure and high flow rate. Analysis of the application and running the drill bit's hydraulics program will indicate which liners to recommend. Finding the specification of the mud pumps allows flow rate to be calculated from pump stroke rate, SPM. Information required: pump manufacturer, number of pumps, liner size and gallons per revolution. Mud condition. Drilling mud has two fundamental functions. The primary function is to keep the well bore in good condition by managing the formations, for example, balancing pore pressure, inhibiting shale reaction, etc. The secondary function is to aid the drilling process, for example, transporting cuttings to surface, cleaning and cooling the drilling bit, etc. For maximum drilling performance, the mud system must be maintained in good condition. Minimum information required: type, OBM, WBM, POBM, silicate, etc. Weight, solids content, PV or YP. Lost circulation material. Lost circulation material is frequently required to plug fractures in the well bore. If these fractures are not plugged, a significant volume of mud can be lost to the formation. Mud is expensive, and losses must be minimized. Lost circulation material comes in various sizes and types, for example, nut plug, cottonseed hulls, cellophane, etc. LCM, as well as plugging holes in the well bore, can plug nozzles in a drill bit. If determined that lost circulation material will be required, ensure that the size and type is known so that drill bit nozzles can be selected that will allow LCM to pass through with a minimal risk of plugging. Surface parameter gauges. Surface parameter gauges are the primary tools for evaluating and setting drilling parameters. Consequently, it is critical that all gauges are operational and calibrated. The following gauges and recording instruments need to be checked: standpipe pressure, RPM, WOB, torque, geolograph, depth measurement, rig floor parameter display or monitor, SPM. Bottom hole assembly evaluation. The bottom hole assembly directly affects drilling performance. The addition of a downhole drive mechanism, motor or turbine can significantly increase penetration rate, while the addition of stabilizers can affect the dropping, building or turning tendencies of the drill string. A rotary steerable system can provide improved directional control compared to that of a motor in some applications, for example, extended reach wells, applications where differential sticking of the BHA is problematic, etc. Useful information is: turbine specification. Revolutions per unit volume pumped for RPM calculation. Due to the mechanical operation of a turbine, the calculated RPM is theoretical and is not necessarily actual RPM. Motor specification. Performance charts. Lobe configuration for motor type, for example, high torque, low speed. Revolutions per unit volume mud pumped for RPM calculation. Stabilizer details can affect both directional tendencies and transmitting weight to the bit, for example, stabilizers hanging up. Details required are size, position in the drill string, including motor stabilizers. MWD, LWD details. Find out the specifications for these tools and what data each is collecting. It is easier to ask or get the data if it is known that it is being collected. Downhole data is better than surface data for problem identification, monitoring, and curing, for example, downhole vibration data. Useful downhole data is RPM, torque, average, maximum and minimum, WOB, pressure, vibration. Preceding bit run evaluation. Find out the details of the preceding bit run. What factors improved or reduced drilling performance, and can the lessons learnt be utilized in the planned run? Find out the condition of the preceding bit when it went in hole, i.e. new bit, rerun, retipped, etc. Be on the rig floor to witness the preceding bit and BHA being pulled through the rotary table. This is the only way of ensuring maximum information is collected on the dull condition of the bit and the BHA, i.e. sometimes bit or BHA balling is removed and not recorded. Collect the run details, dull grade the bit, and take photos as outlined in the dull grading and dull bit photos section. If a detailed run report is required, this information may be critical. If it is planned to run a PDC bit and the preceding bit is pulled out of hole with severe damage, lost cutters or cones, or severely under gauge, the hole should be conditioned with a roller cone bit and a junk basket. PDC bits are generally not recommended for long intervals of reaming or cleaning out junk. Drill bit TFA, total flow area, calculation. System hydraulics can greatly affect drilling performance, for example, HSI and cuttings removal for high ROP, cutter cooling for drill bit life, etc. It is important that both the nozzle and pump liner size are selected to optimize the hydraulics for that application. The limiting factor may be available rig power. The drilling rig motor that drives the mud pumps, combined with the pump liners, sets the maximum standpipe pressure and flow rate available. Making up the bit to the drill string. Flow is the critical medium that cleans, cools, and lubricates the cutting structure and bit, critical for unsealed roller cone bits. In some applications, drilling with minimal flow rate will cause rapid degradation of the drill bit cutting structure. HSI is a primary factor for maximizing ROP. HSI is the energy at the bit that transports the cuttings from the bit face into the annulus. Flow rate is another important factor. High flow rate helps lift the cuttings to surface. Turbulent flow is generally achieved around the drill bit. Laminar flow is generally preferred around the drill string to prevent hole damage. The DDI hydraulics program should be run to optimize the hydraulics for either maximum HSI or maximum flow rate, depending on the application requirement. If there is the possibility of pumping lost circulation material, small jet sizes should not be run, as the risk of plugging them is high. As a general rule, nozzle sizes under 12-30 seconds should not be run. Calculation of expected pressure change if one of the nozzles becomes plugged or is lost. Preparing the bit to run in hole. These are final checks to ensure that the correct bit with the correct nozzle sizes is run whole and is recorded accordingly. Record bit type, size, and serial number. Ensure there is no debris inside the central feed bore and the individual feed bores that could potentially plug a nozzle. Ensure the bit is jetted with the correct size nozzles, as indicated by the drill bit's TFA calculation. If either damaged in transit, a rerun, or a repaired bit, record bit condition dull grade. Photograph the bit, as outlined in the dull bit photos section. Take extra shots of damaged or worn area as necessary. If a motor is to be tested in the casing, recommend using a dull bit rather than the bit required to drill the section. This eliminates the risk of damaging the bit planned for the section in the casing. Ensure that the bit is not manhandled on the rig floor, and if it is damaged, record the incident and damage appropriately. If there is severe damage, it may be necessary to recommend that a different bit be run in whole. Witness the bit and BHA get made up to the string and run through the rotary table. Ensure the bit is handled correctly on the rig floor and not damaged. For example, never place a PDC bit cutting structure directly on the steel decking of a rig floor, as this risks damaging cutters. Ideally, use a wooden or rubber mat. Clean and grease API pin or box connection of both bit and drill string. Using the DDI bit breaker, locate bit in rotary table. Lower drill string onto the bit and engage threads. Either make up by hand or slow rotation. Torque up connection to the specified torque for that API connection. This can be found on the product report that accompanies the bit in the bit box. Running in hole. When tripping, there is little that a field engineer can influence. The rig crew will try and trip in hole as fast as possible to return to drilling. It is worth noting the following points and communicating them to the oil company representative and the driller. Take care running through diverters, BOPs, wellheads, casing shoes, etc. Approach tight spots slowly, as striking ledges can damage the bit cutting structure. When reaming tight spots, pump at maximum flow rate, rotate the string with low rotary speed, 50 to 60 RPM approx, and low weight on bit, no more than 4,000 pounds. In a tight spot, the weight is only supported by the cutting structure towards gauge, resulting in higher weights on individual cutters, insets or teeth than is normally the case. Hence, to prevent cutting structure damage, low weight should be recommended. On the final stand, Kelly washed the hole at full flow to bottom and rotate the string at low rotary speed to prevent plugging a nozzle or balling the bit with cuttings, carvings, etc. that may have collected in the bottom of the hole. Watch for an increase in torque and weight when approaching bottom to identify when the bottom of the hole has been tagged. Lift off bottom 6 to 12 inches at maximum flow while rotating the bit for 5 minutes approx to clear the bottom of the hole. Drilling out the wiper plugs, cement, shoe, and float assemblies. Different types of drill bits and bottom hole assemblies have different drill-out procedures. When designing a drill-out float assembly for PDC applications, PDC-friendly equipment will ensure a successful run, i.e. more plastic and rubber components make for an easier drill-out. Liner running tools and float equipment that require an activating ball to set or close the liner hanger or float valve can cause problems during drill-out. These balls, typically made of brass, can damage the bit, resulting in slower penetration rates and failure to complete the desired interval. Aluminum landing collars can also be problematic. Aluminum in the dart, landing collar, float collar, and float shoe can plug the junk slots of the bit, impairing bit cleaning or cooling, and hence bit performance. PDC, including steering wheel and bicentrics, impregnated and diamond drill bits. Natural diamond impregnated and surface set diamond drill bits will take 25 to 50% longer than PDC drill bits to drill out casing shoe assemblies. Ensure there is no metal or junk in the hole. Do not use automatic driller. Wash and ream to bottom with maximum flow rate at least 30 feet above where the cement is expected. Use 50 to 60 RPM with a rotary assembly and 20 to 40 RPM with a motor assembly. Tag bottom slowly with 4,000 pounds maximum weight on bit and look out for green or wet cement. If the bit does not drill off, reciprocate the drill pipe. Do not stay on bottom if bit is not drilling. Use as little weight as possible. Do not exceed maximum recommended weight on bit. If the wiper plugs begin to rotate, it may be necessary to tag bottom without rotation and increase weight on bit slowly. Do not spud the bit into the float equipment. Once sufficient weight on bit, start with 6,000 to 8,000 pounds and increase as necessary, is applied, slowly increase rotary to 60 to 80 RPM. Repeat as necessary to drill through the remainder of the plugs. Monitor penetration rates and adjust weight on bit as necessary. In difficult drill-out applications, allow the weight to reduce or drill off naturally and evaluate penetration rate. Repeat this process until a more consistent drilling pattern is established. Raise the bit 2 feet off bottom and circulate once the plugs are drilled and midway through drilling the float collar assembly. Repeat as often as dictated by hole conditions or bit performance. Reducing or stopping the flow rate may cause the bit junk slots to pack off. Use extreme caution when reducing flow rates during drill-out. On semi-submersible and drill ships where the rig may heave, use the compensator to prevent spudding the bit. Rig heave can complicate a successful drill-out and can cause bit balling. Roller cone drill bits, insert and milled tooth. Wash and ream to bottom with maximum flow rate at least 30 feet above where the cement is expected. Use 50 to 60 RPM with a rotary assembly and 20 to 40 RPM with a motor assembly. Ensure correct motor has been selected, as very high speeds do not suit some roller cone bits. Do not use automatic driller. Tag bottom slowly with 4,000 pounds maximum weight on bit and look out for green or wet cement. If the bit does not drill off, reciprocate the drill pipe. Do not stay on bottom if bit is not drilling. Use as little weight as possible, increasing to 10,000 pounds if required. Do not exceed maximum recommended weight on bit. If the wiper plugs begin to rotate, it may be necessary to tag bottom without rotation and increase weight on bit slowly. Do not spud the bit into the float equipment. Once sufficient weight on bit, start with 68,000 pounds and increase as necessary, is applied, slowly increase rotary to 90 to 100 RPM. Repeat as necessary to drill through the remainder of the plugs. Monitor penetration rates and adjust weight on bit as necessary. In difficult drill-out applications, allow the weight to reduce or drill off naturally and evaluate penetration rate. Repeat this process until a more consistent drilling pattern is established. Raise the bit 2 feet off bottom and circulate once the plugs are drilled and midway through drilling the float collar assembly. Repeat as often as dictated by hole conditions or bit performance. Reducing or stopping the flow rate may cause the bit cutters to pack off. Use extreme caution when reducing flow rates during drill-out. On semi-submersible and drill ships where the rig may heave, use the compensator to prevent spudding the bit. Rig heave can complicate a successful drill-out and can cause bit balling. Bedding or breaking the bit in. Approach bottom with maximum flow rate. Slowly set the bit on the hole bottom with no more than 4,000 pounds weight and 40 to 60 RPM to establish the bottom hole pattern. Extra care should be taken following a coring run due to the possible stump left on the bottom of the hole. If the bit does not drill ahead, increase weight until it does. Maintain as low weight as possible until the bit has drilled at least its own length. Until the bit has cut its own bottom hole pattern, only some of the cutters will be in contact with formation, so if weight is added too quickly, particularly in hard formations, these cutters may be overloaded and fail. Increase weight on bit to target weight on bit. Do not exceed recommended maximum for the bit. As a general rule, the optimum weight for a PDC is less than half that for a roller cone bit. Increase rotary speed up to target RPM. Making connections and restarting drilling. Maintain full flow as bit is raised off bottom. Return to bottom with 50% of the target drilling rotary speed and full flow rate to wash and clean the hole. Return to bottom gently. Dropping the string too rapidly can cause the bit to tag bottom violently and damage the cutting structure. Increase weight on bit to target weight on bit, taking care to avoid stick slip or other detrimental vibrations. Increase RPM to target RPM. General drilling's parameters for clean formations. Clean formation refers to a homogeneous formation that is not interbedded and is 100% one lithology type. These types of formations are rare, as some shales, for example, include a certain sand and limestone content. However, selecting parameters that suit the primary lithology will generally optimize drilling performance. Soft, clean shales. Increasing rotary speed generally improves penetration rate. Usually, RPM has a greater effect on ROP than WOB. There is minimal risk of damaging the cutting structure in this lithology. Hard, clean chalk or limestones. Penetration rate is maximized by increasing cutter point loading to fracture the formation. High weight is recommended with low rotary speed to allow the cutters to bite into the formation. Bits may suffer impact damage. If the formation is clean, i.e. no sand content, the cutters should suffer minimal abrasive wear. Hard sandstones. Penetration rate is maximized by increasing cutter point loading, so high weight is recommended. To ensure the cutters can get a bite, low rotary speeds are preferred. Bits may suffer both impact damage and abrasive wear. Low RPMs will reduce abrasive wear. Low rotary speeds will also reduce penetration rate, so a reasonable compromise must be reached. Drilled cuttings analysis. Regularly collect and analyze the cuttings coming over the shakers to confirm the formation lithology being drilled. It must be remembered that cuttings coming over the shakers take time to reach surface. This time can be calculated, and the cuttings related to their drilled depth and those drilling parameters. Reviewing the cutting's shape and size can indicate drilling efficiency, i.e., rock flour is very inefficient. Fundamental parameter discussion. Torque. Rotary torque is an indicator of what is happening at the drill bit. For example, PDC high torque. The bit is likely to be digging, or if there is low ROP, the torque could be being generated from the BHA and not the bit. PDC low torque. The bit could be skidding in a hard formation, the cutting structure could be dull, or the bit could be balled up. Roller cone medium torque. The bit is likely to be digging. Roller cone high torque. The bit could have locked cones. If this is the case, the torque will reduce as the inserts or teeth wear down. Roller cone low torque. The cutting structure could be dull or balled up. In soft formations, torque may indicate the bit is on bottom before the weight on bit gauge does. In such formations, the torque gauge may be the best surface measurement by which to drill. The torque could be considered to be too high when it starts to slow down surface rotary speed. The torque is too high when it stalls the motor, rotary table, or the top drive. Homogeneous formations should produce a smooth, constant torque signal. Interbedded formations will provide torque changes as the bit and/or the BHA moves in and out of formation beds that have different rock strength and drillability. If downhole torque measurements are available, they can be used in combination with surface measurements to gain a more accurate representation of what is happening in the well bore. Weight. As a drill bit cutting structure wears, more weight will be required to achieve the same ROP in a homogeneous formation. PDC wear flats, worn inserts, and worn milled tooth teeth will make the bit drill less efficiently. Increase weight in increments of 2,000 pounds approximately. In general, weight should be applied before excessive rotary speed so that the cutting structure maintains a significant depth of cut to stabilize the bit and prevent whirl. If downhole weight measurements are available, they can be used in combination with surface measurements to gain a more accurate representation of what is happening in the well bore. Rotary speed. Total bit rotary speed is equal to the surface rotary speed plus the downhole motor or turbine rotary speed. Rotary speed is not limited when running PDC drill bits. High rotary speed should be avoided in abrasive formations to prevent rapid abrasive wear. High rotary speed should be avoided if the drill bit starts to whirl. Rotary speed may be limited due to drill pipe or drive limitations. Some rotary speeds can initiate drill string resonance, high levels of vibration, and should be avoided. Either increase or decrease RPM to avoid operating in drill string harmonic frequencies. High rotary speeds in hard formations may reduce ROP as the cutters are unable to dig in. The rotary speed that maximizes ROP without causing other drilling problems is likely to be the right one. Flow rate. Flow rate greatly affects hole cleaning. Generally, high flow rates provide better hole cleaning than low flow rates, as they are better able to return cuttings to surface due to increased annular velocity. Flow rate greatly affects bit cleaning. Generally, high flow rates provide better bit cleaning than low flow rates by increasing hydraulic energy at the bit. If a motor is in the hole, increasing flow rate will increase the rotary speed developed by the motor. Increasing motor speed must be considered carefully as it can greatly affect drilling performance. In clean shale, increasing motor speed increases bit speed. That will generally increase penetration rate without damaging the bit cutting structure or other downside. In hard abrasive sandstone, increasing motor speed increases bit speed. That will generally increase penetration rate momentarily. However, the higher rotary speeds will tend to increase the wear rate of the bit cutting structure. That will reduce penetration rate and ultimately bit life. Increasing motor and consequently bit speed can change the directional tendency of the bottom hole assembly with a bigger effect on building or dropping tendency than azimuth. the compromise between instantaneous penetration rate and sliding corrections must be considered. High flow rates can cause formation damage, especially in highly fractured formations, so excessive flow rates must be avoided. Simple drill-off test procedure. The following simple drill-off test has been used since drilling started. It is simple to conduct, has little or no impact on rig time, and the results are immediately apparent. All that is needed is a watch with a second hand, a tally book, and a pen. Basically, at 3 different rotary speeds, weight is applied to a given level and the brake chained down. The weight is then allowed to drill off. Talk to the driller to describe and explain the series of tests to be performed. Select 3 rotary speeds to be tested, for example 80, 120 and 160. Apply the lower rotary speed and increase the weight to the maximum recommended in the bit operating notes. If the formation is known to be soft, a lower weight should be selected to avoid bit balling. If the maximum weight is not achieved before high torque levels or vibration occur, then select a lower weight. Chain the brake down and allow the weight to drill off. Note down the weight on bit that the brake was locked and list below weights in decreasing value, for example 2,000 pounds. Note down the time taken to drill off a weight interval as listed. The least time taken in seconds to drill off indicates the weight that will give the highest penetration rate at that rotary speed. Test the other 2 rotary speeds in the same way. Attention should be made to any vibrations experienced throughout the tests. See Insight. Check with time-based MWD shock data to see if unstable drilling conditions existed at any particular weight and rotary speed combination. Select on the basis of the drill-off tests and shock data the optimum combination of weight and rotary speed. Frequently increasing weight will increase penetration rate. However, if vibration occurs, axial, whirl, or torsional, drilling efficiency is poor, resulting in lower penetration rate. When this occurs, higher penetration rate can frequently be achieved by reducing the weight to minimize the inefficient vibrations. BP Formalized Drill-Off Test Procedures. Summary. Drill-off tests are essential to identify which factors are limiting ROP on a particular bit run and the levels of WOB and RPM that will give best ROP for the constraints acting during that bit run. This section describes how to perform a drill-off test and how to treat the resultant mud logging data to yield clear drilling parameter relationships to ROP, so that the best WOB and RPM can easily be chosen. There are 2 types of drilling test available to relate WOB and RPM to ROP. 1. A drill-off test, where the WOB is built to a selected level, the brake locked, and the bit allowed to drill off as the string extends under its own weight. RPM and flow rate are held constant as the bit drills off, and the drill-off is then repeated at different rotary speeds. ROP is calculated from the rate of WOB decay as the bit drills off, and plotted versus WOB for each RPM. 2. A drillability test, where pairs of WOB and RPM are chosen and a certain depth increment drilled at each pair. Average values of WOP, RPM and ROP are then taken for each interval, and cross plots of ROP versus WOB created, again for each RPM. The first type of test is generally preferred because a range of WOB and ROP data is gathered while the bit drills off over only a very small interval. Thus the results are less likely to be affected by formation changes. The second type of test is, however, useful when prevailing ROP is very high because insufficient, time-based data can be gathered if the bit drills off rapidly at high WOB during the drill-off type of test. The second type of test guarantees acquisition of a minimum amount of foot-based data irrespective of ROP. Both types of test may be limited as to the maximum applicable weight on bit, either by motor stalling when a motor is in use, by weight below the jars, or by torque cycling if the soft torque system is not perfectly in tune. In addition, Varying surface RPM when a motor is in use may be of little value, since small changes in surface speed make little difference to bit speed with a motor in use. Motor speed will probably need to be constant, since a flow rate stipulation will be in effect for hole cleaning. Varying surface RPM when a motor is in use may be of little value, since small changes in surface speed make little difference to bit speed with a motor in use. Motor speed will probably need to be constant, since a flow rate stipulation will be in effect for hole cleaning. Both types of test have been run in BPXC wells since 1993 and have proven useful and relatively easy to perform. The most laborious step involves treating the mud logging data to reduce the contribution of errors in the ROP measurement. To aid this, BP's methods have been built into drill-off test software, which is currently being installed onto Xlog and GeoServices mud logging systems. Since this software is as yet incomplete and not validated, a more generalized method for drilling tests is described next, where data is treated using conventional spreadsheet packages. Optimizing drilling performance. Optimizing drilling performance is frequently interpreted as maximizing penetration rate. However, this is not always the case, as in some applications, drilling performance will be optimized by maximizing run length and reducing the number of trips. In these applications, an example of which is interbedded formulations, the goal is to protect the cutting structure, so it may be necessary to compromise penetration rate for run length. A diligent driller that performs frequent drill-off tests for drilling parameter optimization will always drill further and faster than the driller who sets and forgets. Parameter optimization can significantly reduce cost per foot. Points to note are: be on the rig floor at all crew changes. This is critical to ensure optimum drilling parameters are maintained, to update the new driller of the current drilling or rig issues, and of any drilling parameter testing in progress. If running a motor, try setting the automatic driller to run off motor differential pressure rather than weight on bit. This generally corrects the weight faster. Consequently, the weight will be applied more consistently and better performance achieved. Conduct a series of drill-off tests at various weights, for example, 2 to 5,000 pounds increments, rotary speeds, for example 5 to 10 RPM increments, and flow rate, to change downhole RPM if a motor is in the hole, although care is required as flow rate changes will also affect bit HSI and hole cleaning, to find the optimum drilling parameters to achieve satisfactory penetration rate or to minimize bit or BHA damage. Formation changes can result in a penetration rate change. For example, if the ROP reduces and reasonable torque is still generated, the formation is likely to be harder, so the rotary speed should be reduced and weight increased. If this generates too much torque, weight should be reduced and RPM increased. Monitor mud weight. As mud weight increases, ROP generally decreases. When closer to balanced drilling, where the mud pressure equals the formation pore pressure, ROP generally increases. Maintaining good notes is very important for optimizing drilling performance over an entire run. It also aids understanding or problem solving if the drilling becomes problematic. If this is completed in a spreadsheet, downhole RPM, etc., can easily be calculated and plotted to watch for trends. Parameter readings are more accurate if read directly from the gauges, Martin Decker for WOB, the standpipe gauge for pressure, etc., than those displayed on the rig floor monitor or geolograph. The rig floor monitor and the geolograph can be inaccurate unless they are frequently recalibrated as hole is drilled. Drill-off test method 1. Locked brake test. Planning and supervising the test. 1. Choose the WOB to drill off from or to. Choose upper limit, noting torque cycling, motor stalling, weight below jars, and bit limit from catalogue. Drill off over as wide a range as possible within these constraints. 2. Choose the 3 rotary speeds to be applied, if a rotary BHA. Choose as wide a range as possible, for example 80, 140 and 200 RPM. A lower maximum may be applicable with a tricone bit. 3. Notify the mud logging unit that a test is to be performed. 4. Ensure that the WOB is simultaneously zeroed by the driller and the mud logging unit immediately before the test. Note the reference hook load, string weight values from the mud logging display and the Martin-Decker gauge while rotating off bottom at the same RPM and SPM as will be used during the drill-off test. 5. With the middle RPM value, build the WOB up to the desired maximum, lock the brake, and allow the bit to drill off at a constant RPM, SPM. Lower the desired maximum ROB and restart the test if torque cycling is severe. 6. Repeat step 5 with the highest and lowest RPM, and lastly with the middle RPM. This last repeat drill-off will give some idea if the formation remained constant and if the data quality is good. 7. Return to normal drilling. Instruct the mud loggers to process the drill-off test data. Processing of the data by the mud loggers. During the test, the logging system should run a time database and chart recorder, gathering the following data at an interval not longer than every 30 seconds. Time, block height, hook load, instantaneous WOB, RPM, average torque, sigma torque, flow rate in, pump pressure. These data will be used for the computations described here. Calculate a value for the axial stiffness, compliance, of the drill pipe. Ignore the HWDP and drill collars. The formula is cross-plot average WOB, x-axis, versus ROP, y-axis, for each RPM. Label or code each curve for the RPM value. If the plot is noisy, e.g. attachment 11, repeat the calculations by selecting only intermittent data points, i.e. by expanding delta time. All 4 of the above calculations must be repeated. Repeat the last step with longer time increments until clear ROP-WOB relationships appear. Avoid using excessively long time increments, since the character of the ROP-WOB relationship will be suppressed. A delta time of 1 to 4 minutes will normally suffice. Use the lowest that gives a clear plot. Deliver the cross-plot to the drilling representative or assistant. An example of the spreadsheet calculations is shown on the attachment. Note that on the attachment example, WOB was calculated from the difference between reference hook load and instantaneous hook load, because the raw WOB data was unreliable. Note also how 2 separate sets of ROP and AVG WOB were computed using different delta times. Interpreting the test results. Review the ROP-WOB crossplot. Use the examples on attachments to aid identification of excessive drag or bit dulling. Choose the optimum WOB and RPM, noting any excess torque cycling at high WOB or low RPM, and any WOB or RPM constraints for required BHA directional behavior. If possible, choose the lowest WOB and RPM that gives maximum ROP. If additional loads are applied without any extra ROP, this will only shorten bit life. Note that when informing the driller of the chosen optimum WOB, the value from the crossplot will be the mud logger's value of WOB. Any discrepancy with the Martin-Decker WOB will need to be rectified before the driller is given an optimum WOB. Drill-off test method 2. Drillability test. Planning and supervising the test. 1. Choose the 3 or 4 WOB values to use during the drillability test. Choose the highest WOB, noting torque cycling, motor stalling, weight below jars, and bit limit from catalogue. 2. Choose the 3 rotary speeds to be applied at each WOB, if a rotary BHA. choose as wide a range as possible, for example 80, 140 and 200 RPM. A lower maximum may be applicable with a tricone bit. 3. Notify the mud logging unit that a test is to be performed. 4. Start the test early enough in the drilling of a stand so that making a connection will not be necessary before the test is completed. 5. Ensure that the WOB is simultaneously zeroed by the driller and the mud logging unit immediately before the test. Note the two reference hook load starting weight values from the mud logging display and the Martin Decker gauge while rotating off bottom at the same RPM and SPM as will be used during the drilling test. 6. With the first WOB value, drill 5 feet with each of the 3 RPMs. Abort the test at highest WOB if torque cycling is severe, and restart with lower WOB. Ensure the driller works to maintain as constant WOB as possible. 7. Repeat step 6 with the other WOB values. 8. Return to normal drilling. Instruct the mudloggers to process the drill-off test data. Processing of the data by the mudloggers. During the test, the logging system should run a time database and chart recorder, gathering the following data at an interval not longer than every 30 seconds: time, block height, hook load, instantaneous WOB, RPM, average torque, sigma torque, flow rate in, pump pressure. These data will be used for the computations described here. If any problems exist with these data, conventional depth database data can be used. From the time database or chart recorder data, former is preferred, identify the start and end of each period of constant WOB and RPM. Calculate an accurate average of WOB and RPM for each period when these parameters were held constant. For each period of constant WOB and RPM, calculate an average ROP from the change in block height and the duration of the period. Repeat the calculations for each period of constant WOB and RPM. Cross-plot average ROP, y-axis, versus average WOB, x-axis, for each RPM. Deliver the cross-plot to the drilling representative or assistant. An example of part of a time database dataset from this type of drilling test is shown. The final ROP-WOB crossplot is shown. 2 RPMs were used at each WOB in this case. Interpreting the test results. Review the ROP-WOB crossplot. Use the examples to aid identification of excessive drag or bit dulling. Choose the optimum WOB and RPM, noting any excess torque cycling at high WOB or low RPM, and any WOB RPM constraints for required BHA directional behavior. If possible, choose the lowest WOB and RPM that gives maximum ROP. If additional loads are applied without any extra ROP, this will only shorten bit life. Note that when informing the driller of the chosen optimum WOB, the value from the crossplot will be the mudlogger's value of WOB. Any discrepancy with the Martin Decker WOB will need to be rectified before the driller is given an optimum WOB. Drill string dynamics, vibration. General. Drill string vibration is inevitable. Low levels of vibration can be harmless. Severe downhole vibrations can be problematic and can cause the following: drill string failure, washout, twist-off, premature bit failure, poor directional control, damage to well bore, hole enlargement, rotary drive stalls, top drive or rotary table, motor stalls, motor failure, bearings or stator, MWD failure, stabilizer or tool joint wear, reduced penetration rate. Primary drill string excitation forces are bit or formation interaction, BHA or borehole interaction, downhole motor or turbine, Rotary drive type. The response of the drill string to excitation forces is complex. The complexity of vibration is due to the physical coupling between the bit and the drill string and the coupling of vibration mechanisms. Identify if the rig is equipped with a rotary feedback system, soft torque, and whether it is activated. Types of vibration. There are 3 types of vibration. Axial, motion along the drill string axis. Whirl, eccentric rotation of a component about a point other than its geometric center that can generally be recognized or seen as lateral vibration, side-to-side motion. This can relate to both the bit and the bottom hole assembly. Torsional, motion causing twist, torque, or stick slip. These types of vibration can coexist and produce symptoms that belong to more than one vibration mechanism. This can make the detection process iterative for identification and cure. Drill string resonance. Drill strings have their own natural frequencies for vibration relating to rotary speed. Excitation frequencies close to the natural frequency of the drill string will cause the drill string to resonate, vibrate laterally and/or torsionally. A resonating drill string can be highly damaging to bit or BHA components. Rotary speeds that induce and sustain drill string resonance should be avoided. Axial vibration. General. Severe axial vibration leads to bit bounce. Vibration range is 1 to 10 Hz. 1 Hz is equal to 1 vibration cycle per second. Most frequently occurs when drilling with roller cone bits in hard formations. Occasionally occurs with PDC drill bits in hard formations. Caused by weight on bit fluctuations. Extreme WOB variance can cause the bit to lose contact with the bottom of the hole and then impact back to bottom. The 3 cones of a roller cone bit will generate a tri-lobe pattern, causing the bit to be axially displaced 3 times per bit revolution. Can be caused by formation change. Detection. Large surface vibration. Axial movement of pipe at surface. Large weight on bit fluctuations. High levels of axial vibration from MWD tools. Consequences. Bit damage, including cutting, structure, bearings, seals. Reduction in penetration rate. Short run lengths. BHA washout. MWD failures. Cures and control. Destroy tri-lobe bottom hole pattern by either changing drilling parameters, lifting off and returning to bottom with lower weight and lower rotary speed. Run a shock sub in the BHA. Running shock subs with PDC bits is not recommended as they can lead to bit chatter, high-frequency vibrations that can chip and prematurely fail PDC cutters. Bit whirl. General. The eccentric rotation of the bit about a point other than its geometric center. Whirl is a self-perpetuating motion. Types of whirl. Forward whirl. The center of rotation rotates in the same direction as the drill string, causes flat spots on stabilizers and tool joints. Backward whirl. The center of rotation rotates in the opposite direction to the drill string, is more violent than backwards whirl, and can cause severe cutting structure damage. Chaotic whirl. The whirl rotation moves between forward and backward whirl. Can generally be recognized or seen as lateral vibration, side-to-side motion. Whirl induces high-frequency lateral or torsional vibrations in the range of 10 to 50 Hz. 10 Hz is equal to 10 vibration cycles per second. Causes a dramatic increase in impact loading on the bit cutting structure, causing rapid failure. Motors with bent housings can cause whirl. Can be initiated by formation change. Frequently seen while reaming. BHA whirl can induce bit whirl and vice versa. Detection. Can be difficult to detect at surface. Generally seen at high RPMs and low WOBs. Increased surface and downhole torque. High-frequency downhole lateral or torsional vibration. Increase in MWD shock counts. Reduction in penetration rate. Over-gauge hole. Cutter impact damage, generally over the shoulder and gauge areas of the bit. Consequences. Bit damage, cutting structure damage, generally over the shoulder and gauge areas of the bit. Reduction in penetration rate. Short run lengths. BHA washout. MWD failures. Motor failures. Cures and control. Reduce rotary speed and increase weight on bit. Ream at lower rotary speeds. Destroy bottom hole whirl pattern by either changing drilling parameters, lift off bottom and attempt to restart drilling without initiating whirl. Try high WOBs and low RPMs. Run anti-whirl or steering wheel bit. Run higher torque and lower speed motors so that higher weights can be applied. Run roller reamers instead of stabilizers. BHA whirl. General. The eccentric rotation of the BHA about a point other than its geometric center. Whirl is a self-perpetuating motion. Types of whirl. Forward whirl. The center of rotation rotates in the same direction as the drill string, causes flat spots on stabilizers and tool joints. Backward whirl. The center of rotation rotates in the opposite direction to the drill string. Chaotic whirl, where the bit moves between forward and backward whirl. Can generally be recognized or seen as lateral vibration, side-to-side motion. Initiated by friction between stabilizers or tool joints and the well bore, leading to gearing of the BHA around the hole. Whirl induces high-frequency lateral or torsional vibrations in the range of 5 to 20 Hz. 5 Hz is equal to 5 vibration cycles per second. A stabilizer passing a ledge or through a formation change can initiate BHA whirl. Mud properties greatly affect BHA whirl, as the mud is the lubricant that reduces friction between the stabilizer or tool joint and borehole wall. Bit whirl can induce BHA whirl and vice versa. Detection. Can be difficult to detect at surface. Increased surface torque. High-frequency downhole lateral torsional vibration. Increase in MWD shock counts. Localized wear on stabilizers and tool joints. Damage to stabilizer blades. Cures and control. Change drilling parameters. Reduce RPM and raise WOB. Increase mud lubricity. For example, pump uphill. Run roller reamers or non-rotating stabilizers. Run non-rotating drill pipe protectors. Lift off bottom and attempt to restart drilling without initiating whirl. High weights and low RPMs should facilitate this. Torsional vibration. General. Severe torsional vibration leads to stick slip. Stick slip vibration range is below 1 Hz. 1 Hz is equal to 1 vibration cycle per second. Stick slip is the rotary acceleration and deceleration of the drill string. The bit can stop rotating momentarily at regular intervals, causing the drill string to wind up and the torque to increase. The drill string will then break free and accelerate the bit to high rotary speeds with minimal torque. Stick-slip motion is often accompanied during its slip phase by lateral vibration of the BHA. Most common with PDC drill bits and can cause severe and rapid damage to their cutting structures. Can be formation dependent. Can be caused by the interaction of the bit and formation, the BHA and the borehole, for example, stabilizers digging into a soft formation, the drill string and the borehole, for example, high well bore tortuosity. can be caused by the drive system characteristics. Generally occurs at low rotary speed and high weight on bit. Detection can be detected at surface by both torque, max min torque greater than 20% mean torque, and RPM variance. Increased surface mean torque. Rotary drive stalls, rotary table or top drive. Increase in MWD shock counts. Downhole RPM can range from 0 up to 2 to 3 times surface RPM. Bit impact damage, cutting structure damage generally seen over the nose of the bit. MWD tool failure. Reduced penetration rate. Over-torqued connections, washouts and twist-offs. Connection back-off due to backward rotation. Downhole memory data acquisition and analysis. Cures and control. Change drilling parameters, increase RPM and reduce WOB. Increase flow rate for increased motor RPM and increased lubricity or reduced friction due to improved hole cleaning. Run rotary drive system, rotary table or top drive, in higher gear. Run a soft torque system. This consists of a top drive or rotary table feedback mechanism that regulates surface torque fluctuation by altering rotary speed, thus enabling more uniform bit rotation. The system must be regularly tuned to take account of changing parameters, including depth and formation. Increase mud lubricity, for example, pump a pill. Run a motor to decouple the drill bit from the drill string and to increase bit RPM. Run roller reamers or non-rotating stabilizers. Lift off bottom and attempt to restart drilling without initiating stick slip. High RPMs and low weights should facilitate this. Vibration coupling. Vibration mechanisms can be coupled since some can trigger others. For example, bit whirl can be triggered by high bit speeds generated during stick slip motion. Stick slip can generate lateral vibration of the BHA as the bit accelerates during the slip phase. Large lateral vibration of the BHA into the well bore can cause bit bounce. Bit whirl can induce BHA whirl and vice versa. Bit torsional vibration can induce BHA torsional vibration and vice versa. Vibration monitoring. General. It is essential to establish what vibration mechanism is occurring downhole in order to prescribe the correct remedial actions. Corrective actions for one may exacerbate another. For example, the corrective actions for bit whirl are directly opposite than those for stick slip. Tool inspection. The nature of damage to downhole drilling components can often be a direct indication of the vibration source and mechanism. For example, the location of bit impact damage could suggest bit whirl or stick slip, shoulder and gauge for whirl, nose and face for stick slip. Flat spots on tool joints are evidence of forward whirl. Damage to stabilizer blades is an indication of BHA whirl and lateral vibration. Mud logging data. Mud logging data can provide the following surface measurements: mean torque, max or min torque, RPM, WOB, flow rate. This data gives a good indication of whether stick slip is present, i.e., separation between max and min torque is indicative of stick slip type vibration. To improve accuracy, set the chart recorder speed between 0.1 to 0.3 feet per minute. MWD data. MWD data can serve as an invaluable real-time monitoring system. An increase in the number of lateral shocks above a threshold value, usually set at 25 Gs, provides a direct indication of severe BHA lateral vibration. Schlumberger D&M, Baker Hughes Intech, and Sperryson provide MWD tools with shock measurements. Other downhole measurements that give a true indication of whirl or stick slip at the bit rate are RMS torsional vibrations, RMS axial vibrations, RMS lateral vibrations. Gamma ray can indicate if any of the vibration mechanisms are related to lithology, i.e., correlate formation changes to vibration changes. If a rock strength analysis is completed, both gamma and sonic required as minimum, it may indicate if rock strength is inducing the vibration mechanisms. LWD or wireline log. Caliper data indicates hole oversize and provides evidence for either bit or BHA whirl. High-frequency surface measurements. High-frequency surface measurements of axial and torsional vibration can help indicate bit whirl, especially in shallow and non-deviated wells. Baker Hughes Intec can provide these measurements. Downhole recording. In deviated wells, it is not usually possible to detect high-frequency events such as bit whirl from surface measurements due to dampening and attenuation of lateral vibrations. Downhole recording of the vibration data can be analyzed for subsequent wells. Schlumberger, DRT, and Sperry-Son can provide downhole vibration measurement recording tools. Factors related to bit run termination. Economics. Frequently assess the run economics for the benefit of the operator. For example, at a formation change, it may be more economical to replace an insert bit with a faster PDC bit, even though the insert bit still has many operating hours left. It may be more economical to pull a bit early to achieve a shorter trip and then complete the section with a longer final run. Worn cutting structure. Cutting structures wear out: PDC, insert, milled, impreg, diamond. A worn cutting structure requires more weight to achieve the same penetration rate as a new, green cutting structure, i.e., ROP generally decreases. If the gauge area of the cutting structure wears first, the bit can become a wedge-shaped plug that fits tightly in the hole. This can cause high on-bottom torque, even with low weight on bit, very low penetration rate, and often accompanied by an increase in SPP. Undergauge bits can also cause the stabilizers to hang up and cause general BHA damage. As an impregnated or surface-set diamond bit wears, the standpipe pressure will increase due to a reduction of the flow area. This is due to a reduction in blade height due to wear. As a PDC bit wears, for a given weight on bit, torque generally reduces as the cutting structure is no longer as aggressive. Severe PDC wear can result in the blades being worn down to the bit body or nozzles. Consequently, a significant increase in SPP will be seen as the flow is restricted due to contact of the bit face and the formation. Worn or failed bearings on roller cone bits. If it is thought that the bearings have failed, the bit should be immediately pulled. Failed bearings can deteriorate rapidly and result in losing a cone downhole. This is a very serious and expensive failure for the oil company due to lost time fishing. There are various symptoms that suggest a bearing failure. For example, torque changes, spikes, character or overall level not related to parameter or formation changes. ROP changes, not related to parameter or formation changes. The ROP can increase temporarily as the skew angle of a cone increases with a failed bearing. Directional responsiveness change, loss in control of tool face. MWD signal quality deteriorates as the vibration from the bit masks the signal. Bit balling usually occurs when drilling soft sticky formations with WBM. Some formations, predominantly shales, react with water swelling considerably and becoming sticky. Montmorillonite changes to illite with time and temperature. Kaolinite does not hydrate and react with water. The order of claystones with greatest to least balling tendency is Montmorillonite, mixed layer, Montmorillonite, and illite. Illite, kaolinite. Swollen and sticky cuttings can adhere to the bit, clogging up waterways, junk slots, individual cones, and possibly the entire bit. Severe balling results in total clogging up of the cutting structure, so that the string weight is transmitted to the formation via the balling material rather than the cutting structure. Consequently, penetration rate is dramatically reduced. Balled formation can also plug the annulus so that no cuttings can be returned to surface. This results in an increase in SPP and possible risk of losing mud into the formation. Balled bits are generally characterized by reduced rotary torque, reduced penetration rate, increased SPP. If it is thought a bit is balling up, lift off bottom immediately. Drilling with a balled bit can only exacerbate the problem by forcing more material to plug the bit or annulus further. This tightens or compresses the material and makes it heavier and more difficult to transport back to surface. Methods for unballing a bit are: increase flow rate to the maximum for at least 5 minutes. Spin the bit as fast as possible to fling the material off. Lift and drop the string rapidly to shake the formation off. Take care not to surge the hole and damage the formation, or drop the bit on bottom and damage the cutting structure. Pump a pill, for example nut plug, to try and wash the material off. A combination of the above. When returning to bottom after unballing a bit, use maximum flow rate and high rotary speed. Tag bottom gently, as there may be huge chunks of balled material that need to be cut up. If weight is added too quickly, the bit may just push into the balled material and become immediately balled again. Where balling is expected, the risk of occurrence can be reduced by limiting penetration rate. This means that a reduced and more manageable amount of cuttings can be transported away from the bit face and annulus to surface. Lost nozzle. A lost nozzle will cause a sudden decrease in pump pressure. Calculation will indicate the expected pressure drop. Pressure may continue to decrease gradually in an erosive environment due to the nozzle feed bore washing out and increasing in size or cross-sectional area. If penetration rate is not significantly reduced, drilling can continue, but may result in cutting structure damage due to drilling on tungsten carbide nozzle components. In softer formations, a lost nozzle may be pushed into the whole wall and cause minimal cutting structure damage. If a nozzle is lost, HSI is reduced, so there is an increased risk of bit balling and reduced ROP. Plugged or blocked nozzle. Nozzles can be plugged by a variety of materials. Some examples are formation, lost circulation material, motor stator rubber. A plugged nozzle will result in increased SPP. If penetration rate is not significantly reduced, drilling can continue. If multiple nozzles are plugged and there is a severe deterioration in ROP, it should be attempted to unplug the nozzles or pull the bit out of hole. Methods for unplugging a bit are: increase flow rate to the maximum for at least 5 minutes. Lift and drop the string to shake and surge the plugging material free. Take care not to surge the hole and damage the formation, or drop the bit on bottom and damage the cutting structure. A bit with plugged nozzles has an increased probability of balling in softer formations and accelerating cutter wear in abrasive formations. Downhole motor or turbine failure. A downhole motor or turbine failure will dramatically reduce penetration rate. SPP pressure fluctuations are likely to occur as the failure develops. A reduced pressure differential, the difference between on and off bottom pressure, over the motor or turbine is likely to be seen. Depending on the failure, even if the rotary drive is rotating the string, there is a high probability that the bit will not be turning. This is because the motor or turbine may not be able to transmit any torque to the bit. Catastrophic motor failures can be caused by repeated motor stalling. Motor and turbine failures can be caused by bit whirl, stick slip, BHA lateral vibration, etc. At surface, motor bearing wear can be estimated or measured by examining the play in drive shaft. Dull grading. Witness the bit and BHA being pulled out of hole as evidence for run analysis can be collected. Take photos if necessary. For example, all the tool joints worn on the same side suggests forward whirl. BHA balling. Roughnecks will frequently clean the BHA off, and this information will be lost and not recorded. Bit balling. Roughnecks will frequently clean the bit off, and this information will be lost and not recorded. Dull grade the bit using the IADC system. Dull grading manuals for each drill bit type can be found on the SLB website. Roller cone bits and fixed cutter bits have different sized gauge rings. Ensure that the correct gauge ring is used, i.e., if an in-gauge PDC bit is measured with a roller cone gauge, it will appear to be under gauge. Dull bit photo. Use a digital camera so that the photos can easily and quickly be emailed to the product center's DEC or optimization engineer if necessary, and for easy manipulation in a run report. Ensure good quality close-up photos are taken. Number each blade with a marker pen to aid photo analysis at a later date. Take the following photos to ensure the full dull bit condition is recorded: face view, side view, blade by blade, close-ups of any extraordinary cutting structure damage, body junk damage, etc. Run reporting. If good notes are maintained throughout the run, a good report can easily be written. It is good practice to write the report as the run is progressing, so relevant points are highlighted and not forgotten. On the report, it is important to record